Okay, so this is problem 6 out of the textbook. It says an astronaut must journey to a distant planet, which is 200 light years from Earth. What speed would be necessary if the astronaut wishes to age only 10 years during the round trip? Okay, so first off, if you wouldn't mind, please subscribe. And yeah, let's go ahead and get into it. So this is obviously a time dilation question. It's pretty obvious they're talking about the age of the astronaut. So let's write down that equation to start. Delta T equals delta T naught gamma. And then, if we remember, gamma is 1 over the square root of 1 minus v squared over c squared. Sometimes you'll see v over c as beta, but I'm not going to write it like that. I'm going to write it out a little bit more. So delta t equals delta t naught divided by 1 minus v squared over c squared square root. Okay, so we have that. Now let's look at what we have. So it mentions that the astronaut wishes to age only 10 years. Okay, so that's some sort of time. Which time is it? Well, if we have this rocket ship and the astronaut's in it, delta T naught is the proper time. That's the proper time. That would be the time experienced by the astronaut in this case. So delta T naught would be 10 years. So that will be 10 years. Another way you could remember this is your proper time is always going to be less than your actual time. I talked about that in a few videos. We've gone through a couple of these. That was actually a length contraction, but it's a similar idea. I think this one had some time dilation. But that is your proper time. That's going to be obviously the shorter time period, the time period experienced by, in this case, the astronaut. Okay? So we know that's equal to delta T naught. Okay. Well, what is delta T, though? Delta T, we can find that by using simple kinematics. Distance equals rate, which I'm calling v, times time. Or just rearranging it, time equals distance over velocity. So this time is obviously different than the proper time. And this is the time that you would measure maybe if you're watching from Earth. Earth would have a different time. So that's what we're using here. That's why we don't have to use any sort of relativity because of the Earth's reference frame. So it's a lot of reference frame stuff here, but hopefully that makes sense. It's because we're dealing with the Earth's reference time and they're watching the spaceship move from their point of view. They're going to use this time. Now, one thing to keep in mind, and this has got me, I think when I took this class, this was a question I saw on homework, is it's a round trip. So I kind of just plugged in numbers blindly, and I said the distance was 200 light years. Well, that's from the Earth to this distant planet. But if you're going there and back, then the distance is actually 400 light years. That's what the LY stands for. So nothing too crazy there. That'll just be, I guess, a wording question you can consider. So let's go ahead and plug in what we have. This can be plugged in here now. So we have d over v equals, I'm going to keep calling it delta T naught. And if you wanted to, you could call this delta T, and then you could call this, say, delta X if you wanted. I'm not going to do that, but you could if you wanted. I'm just going to call it, I know it's a little weird because the we're using a delta here. I mean, there is still technically a delta. I'm just being lazy. So hopefully you're okay with that. And then I'm going to cross multiply. I could just call that T naught 2, but too late. So now that I cross multiplied and got rid of the fractions, I'm going to square both sides to get rid of the radical. So that gets me d squared 1 minus v squared over c squared equals delta T naught squared v squared. I can distribute this d squared to get d squared minus v squared d squared over c squared. And then what I had over on the right-hand side, that doesn't change, I just distributed. And now I want to get my velocity, since that's what I'm ultimately solving for, on one side. So I'll add over the v squared d squared over c squared. So if I add that over, I now have this. And now I see both of my terms on the left have a, well, they both have a v squared in them, which is fine. So let's factor that out. If I do that, I'll be left with d squared over c squared plus delta T naught squared. And then I can just divide it over. So we have d squared over c squared plus delta T naught squared equals v squared. And then if I just square root both sides, I get v is equal to, well, you'll just have your d there because the square root of d squared is just d. And then in the bottom, we have to be a little careful because we have addition. So we'll just square root that, which is fine. And I'm going to go ahead and just plug in the numbers real quick so you can see kind of how it would be plugged in. For d, it's 400 light years. Remember, it's a round trip, so that's 400 times c over 400c squared over c squared plus, I forgot what it was, I think it was like 10 years squared. And obviously, I think you can see that these c squareds will cancel. So I'm going to plug this in really quick. So when I do that, I get I'll do it in red since this is the answer, 99969, and then I still have this c here. So I just plugged in all the numbers, c times c. Or you could think of it as being 99% the speed of light. So he's really going to have to move if he only wants to experience 10 years. So the big thing with this is just reading the problem and understanding what it's saying. It should be clear it's a time dilation problem. Don't let round trip trick you like it did for me when I took this class. That is there and back, so that's not 200 light years, that's 400. That's just the wording of the question. And then understand the proper time and the diluted time. Two different, or the proper time and delta t and delta T naught. Those are your two different delta t's. So those are two things you're going to have to consider. The proper time in this case will be the astronaut's reference frame. And we're doing that because the astronaut wants his time to be diluted to only 10 years. So that's why that's delta T naught. Delta T, you could think of that as being the time if somebody was here on Earth. Obviously, that's not a good Earth because Antarctica and the North Pole aren't green, but it's fine. And this man's obviously not that tall. He would be a giant. But if he was watching, that would be his time if he had a clock there. And for him, there's no problem using just normal kinematics. So we can rewrite delta t, or I was lazy, so I just called it t, as d over v. Substitute that in here. And then it's just algebra, solving for v and plugging in your numbers. So hopefully that helps.